In the realm of modern computing, the distinction between CPUs with threading and those without threading plays a critical role in determining system performance, multitasking capabilities, and overall efficiency. Understanding how these technologies work provides valuable insight into how processors handle workloads and what makes one CPU outperform another in certain tasks. In the last video, you heard me say that a quad-core processor handles 4 tasks simultaneously, but then you also heard me talk a little bit later about threading and it enabling a single core to handle 2 tasks. Now, threading refers to a CPU's ability to execute multiple threads, the smallest unit of processing tasks within a single physical core. A thread represents a sequence of events that can be managed and executed independently by the CPU. Threading technologies like simultaneous multithreading, SMT, most famously implemented as Intel's hyperthreading, allow a single physical core to manage multiple threads concurrently. CPUs with threading leverage technologies like hyperthreading to increase parallelism. By enabling each physical core to process multiple threads simultaneously, these CPUs improve performance, particularly in multi-threaded applications. In a CPU with threading, each core has multiple logical processors, also called logical cores. For example, a quad-core CPU with hyperthreading will have 8 logical cores. The CPU shares resources like cache and execution units between threads, allowing better utilization of idle resources. More threads mean more tasks can be processed concurrently. Software like video editing, 3D rendering, and server applications benefit significantly, and idle CPU resources are used more effectively. There are, however, some limitations. Not all tasks benefit equally from threading. Some workloads are just inherently single-threaded. You also have increased power consumption. More threads can lead to higher power usage and heat generation, and threads share CPU resources, which can lead to contention and reduced efficiency if not managed well. CPUs without threading execute 1 thread per core. These CPUs rely solely on physical cores to manage tasks, meaning the number of tasks processed simultaneously equals the number of cores. In a CPU without threading, each core handles 1 thread. A quad-core CPU in this case, without threading, will process 4 threads concurrently, or 4 tasks. These CPUs focus on raw core performance, often optimized for single-threaded applications. There's less complexity, and it can lead to better performance in single-threaded tasks. Fewer threads means less power usage, which is ideal for energy-efficient systems. And each core dedicates its resources to a single thread, reducing conflicts. Of course, however, fewer concurrent threads means less efficient multitasking. And tasks like rendering, data processing, and scientific computing won't benefit as much. CPUs with threading are ideal for environments that require handling multiple tasks simultaneously, like video editing, gaming, and server operations. CPUs without threading may outperform threaded CPUs in tasks that depend on raw core performance, such as legacy software, some embedded systems, and some simple desktop applications. In mobile devices and embedded systems, threading might be avoided to save power, while high-performance desktops and servers prefer threading for maximum throughput. The choice between CPUs with threading and without threading depends on the intended use case. While threading offers the better multitasking and improved performance for multi-threaded applications, CPUs without threading may excel in power efficiency and single-threaded workloads. Understanding these key differences helps to select the right processor for specific needs, whether for gaming, professional work, or energy-efficient systems.